Okay, in this tutorial we'll be looking at setting up timers and using interrupts as well. So this first one, we need to write a setup function. So we need to write as a function to set up timer 0 on the MSP430, and we need to generate an interrupt every 35 milliseconds, and we've got a 1 megahertz clock that we're using here. So let's write our function. We'll call it a net timer or something like that. We don't pass any parameters to it, and we don't have any return value from it either. Now, one thing that we need to do is we need to work out how many cycles that we're going to be stepping through based on our 1 megahertz clock. So we can work that out pretty simply. So 1 megahertz clock, that will give us 1 microsecond per timer count if we're not scaling it at all. And our desired delay is 35 milliseconds, or 35,000 microseconds. So essentially our TA0 CCR0 register we can set to 35,000. Now if the number that we're wanting to do was too big for that register, so it was greater than a 16-bit number, 65,535, we need to scale the clock somewhere and slow the timer down. So then we need to use the control register TA0 CTL, and if we put the value 0 to 10 in there, that will put it into, that will enable the SM clock, so our submaster clock, which is what we use generally for these, and it will put it into up mode. Now we remember in up mode the timer will count until it hits TA0CCR0, then it will reset to generate an interrupt, and it will count up again until it hits there. And so that's why we can very easily use this value here in TA CCR0 to control how often we're going to generate interrupts. Now we need to actually turn on the interrupts. So TA0 CCTL0, in here we set this to that. Now that will enable interrupts for this timer. So that will enable interrupts for the TA0 CCR0 compare register. And final thing we need to do is we need to enable interrupts globally. So we say eint and we enable interrupts. Okay, next one, we need to write the interrupt service routine that will be generated from question 1. So this is a very simple interrupt service routine. Checks the value of a particular pin. If it's high, we set another pin high. If it's low, we set another pin low. I guess the tricky part here is actually writing the interrupt service routine, because the code inside it is pretty trivial. So we say pragma vector is equal to, and it's the timer zero vector that we're interested in. We'll give it a name, timer interrupt service routine. Now We can't pass any parameters to it, doesn't have any return value. And then inside here we need some sort of an if condition to do this section of it. So if 0 is equal to P1 in and bit 3. So if it's low, we set this one low, P2 out and equals not bit 4, else we set that bit high. This time, instead of generating an interrupt inside our microcontroller, we're going to be generating a signal specifically on a pin. So we're using P1.2, which is pin 4 of our MSP430. And we need a waveform that is 50 milliseconds period and a duty cycle of 4060. So let's first set up that pin. So P1 dir we'll set as an output. We also need to enable the special function of that pin to actually connect it through to the timer. Otherwise the timer will be trying to drive it but won't actually be able to drive it. So that enables a special function. Now with this one, the easiest way to set these up is probably use up-down mode for our microcontroller. Now remember, up-down mode basically counts like this, and we can have two values, one value here and one value here. This one is our TA0CCR0 register. This one's our TA0CCR1 register. And what we can do is we can use one of them to, oops, sorry, this one should be at the top value there. This is what we count up to, and so our total period will be double the distance from there to there because it has to go back down again. And at one point here we'll do a flip, and then we'll do a flip when we hit that again, whichever direction that we're going in. So let's work that out. We've got a period of 50 milliseconds, and so we need to put half of that in this value here, because if we think about the time taken from there to there, it's double because it needs to count all the way down and all the way up again. So TA0CCR0 is equal to 25,000. 1 megahertz clock, 1 microsecond per clock cycle, and we need 25,000 of them to make up the 25 milliseconds. Now we need to work out our off time. And what we can say is we're interested in 50 milliseconds times 0.6 because 60% off, and then times 0.5 because we're halving it just like we did with our period, 50 milliseconds to 25 milliseconds. So the value that it gives us is 15,000. Now we need to set the output as toggle select. So TA0 CCTL1 So that will connect it to the output pin, and then we need to actually start the timer and set up the clock and everything like that. So that will put the 1 megahertz SM clock and put it into up-down mode. Okay, this last one, we've got a square wave being fed into P1.5. We want to write interrupt to count the number of low to high transitions, so that's what we're interested in, that are occurring. And we have some sort of global variable called counter, and we increment that as well. So let's define the global variable first. If we're defining a global variable and we want to access it and modify it within an interrupt, we need to make it a static volatile global variable. So static vol we're calling it counter. Okay, so let's have our main function where we're setting things up. So we need to set that particular pin as an input. So all the other pins are set as outputs. We need to enable interrupts for that one. So P1 interrupt enable is equal to bit 5. We need to say it's positive edge triggered rather than negative edge triggered. Positive edge triggered will give us this. P1 IES equals 0. If we put a bit 5 in there or set that particular bit to 1, it would make it negative edge triggered. Now we need to clear all our interrupt flags so we don't generate an interrupt immediately, and we need to enable interrupts. Okay, having done that, we can write our interrupt service routine. Now, because this interrupts on port 1, we use the port 1 vector. We say interrupt. We don't have a return value. We'll call it pulse counter, because that's essentially what we're doing. We're counting a number of pulses as they come in. We don't have any value that we pass to this. And essentially what we want to do is we want to increment this counter plus plus, and the only other thing we need to do is we need to clear our interrupt flags because they're not automatically cleared, so we clear that before we leave, and we're done.